Welcome to Tech Girl Kannada YouTube channel. Module 5 Graphs Definitions, Terminologies, Matrix, Adjacent List, Representation of Graphs, Elementary Graph Operation, Traversal Methods, Breadth for Search, Depth for Search, Sorting and Searching, Insertion Sort, Radix Sort, Address Calculation Sort, Hashing, Hash Table, Organization, Hashing Functions, Static and Dynamic Hashing, File and their Organization, Data Hierarchy, File Attributes, Text Files and Binary Files, Basic File Operations, File Organization and Indexing. A graph G consists of two sets, V and E. V is a finite non-empty set of vertices. E is a set of pairs of vertices. Pairs are called edges. So, V of G, E of G represent the set of vertices and the edge. G is equals to VE to represent graph. In an undirected graph, the pair of vertices representing any edges are ordered. For example, UV and VU represent the same edge. In the directed graph, each edge is represented by a directed pair. That is UV, U tail, V is the head. And VU and UV represent different edges. Then we have graph C2, G1, G2 tree, G1, G3, G2 and everything. Edges of a directed graph are drawn within an arrow from the tail to head. As shown in the figure, self-edges and self-loops. In an undirected graph, maximum number of edges in n vertex, any n vertex is n into n minus 1 by 2. N into n minus 1 by 2. In directed graph, it will be n into n minus 1. Maximum number of edges. Subgraph of a G is a graph G dash such that V of G belongs to E of G. E of G bar belongs to E of G. The path from vertex U to vertex V in the graph G is a sequence of vertex U, I1, I2 to IN, V. That is U1, I1, 1 square, I2, then K, V are the edges in the E of G. The length of the path is the number of edges in it. The simple path is a path in which all vertices except possibly the first and the last are distinct. A cycle is a simple path in which the first and last vertices are the same. In an undirected graph G, two vertices U and V are said to be connected if and only if there is a path between U and V. A tree is connected acyclic graph. A directed graph G is said to be strongly connected if and only if every pair of distinct vertices U and V in V of G there is a directed path from U to V. And also from V to U, graph G3 is not strong connected as there is no path from vertex 2 to this. Strongly connected component is a maximum subgraph that is strongly connected. G3 has two strongly connected components. Degree of a vertex is the number of edges incident to the vertex in directed graph. In degree of vertex V, number of edges for which V is the head. Out degree, number of edges for which is the tail. Vertex 1 has in degree 1, out degree 2, and degree 3. In degree 1, out degree 2, and degree 3. The total degree is 3. If di is the degree of vertex in a graph G with n vertices and e edges, then the number of edges is E equals to I0 to n minus 1 sigma di by 2 plus d naught di plus d2 by 2 plus 2 plus 3 plus 1 is equals to 6 by 2 is 3. For 4 nodes, it will be 3 plus 2 plus 3 plus 2 by 2 plus 5 edges. Graph, undirected graph, digraph means directed graph. ADT of graph is ADT graph is objects, a non-empty set of vertices and a set of undirected edges where each edge is a pair of vertices function. for all graph belongs to graph U, V1 and V2 vertices. Functions for all graph belongs to graph. Graph create, return an empty graph. Graph insert vertex. Return a graph with vertex. V inserted. V has no incident edges. Graph insert edge. Graph V1, V2. Return a graph with a new edge between V1 and V2. Graph insert vertex. Graph insert edge. Graph delete vertex. Return a graph in which V and all edges incident to that are removed. Graph delete edge. Graph V1, V2. Return a graph in which edge V1, V2 is removed. Leave the incident nodes in the graph. Boolean is empty of graph if graph equal to empty graph, return true, else return false. List adjacent of graph V, return a list of all vertices that are adjacent to V. Abstract data type is a data structure, is a data type whose behavior is defined with the help of some attributes and some for usually write these attributes and for inside a clear or structure to use an object of the clean to use the partition. Abstract data type. Graph representation adjacent matrix. G is V, E, be a graph with n vertices, n greater than or equal to 1. AM of a G is a 2D n cross n array. Say A, Ij equals to 1. If and only if the edge Ij is in the graph, then Aij equals to 0. If there is no such edge in G, adjacency matrix for an undirected graph is symmetric, edge Ij and edge Ji. AM for a directed graph may not be symmetric. Space needed to represent a graph using its AM is in square bits. For an undirected graph, the degree of any vertex I is its then outer edge degrees. For a directed graph, the row sum is the out degree and the column sum is the in degree. Then adjacency list. N rows of AM are represented as an chains. There is one chain for each vertex in G. The nodes in chain I represent the vertices that are adjacent from vertex. The data field of a chain node stores the index of an adjacent vertex. Vertices in each chain are not required to be ordered. Adjacent list of I is a pointer to the first node in the adjacency list for vertex. Vertices in each chain are not required to be ordered. Adjacency list of I is a pointer to the first node in the adjacency list for vertex. The degree of any vertex in an undirected graph may be determined by just counting the number of nodes in its adjacency list. For a digraph, the number of list nodes is only E. The out degree of any vertex may be determined by counting the number of nodes on its adjacency list. Every connected graph has a spanning tree. Its Kruskal algorithm, prime algorithm are designed to undirected graphs only. Elementary graph orientation. Depth first search is similar to pre-order. Breadth first search is similar to level order. Depth first search. Begin the search by visiting the start vertex V. Visiting consists of printing the node's vertex field, select an unvisited vertex from VCL and carry out a DFS on W temp. Preserve the current position VSAL by placing it on a stack. Eventually, search reaches a vertex U that has no unvisited vertices on its AL. Remove a vertex from the stack and continue processing the AL. Previously visited vertices are discarded, unvisited vertices are visited and placed onto the stack. Search terminates when the stack is empty. void DFS into V, note temp visited of V equals to 1, print percentage dV for temp equal to A of V, temp not equal to null, temp is equals to temp link. If visited of temp info equal to 0, then DFS of temp info. For temp equal to A of V, temp not equal to null, temp equals to temp link. Breadth first search will starting at vertex V and make it as visited. It then visits each of the vertices on V's adjacent list. After visiting all vertices on V's adjacency list, visit all the unvisited vertices of that adjacent to the first vertex of the V's adjacency list. After visiting each vertex, place the vertex in queue. After exhausted an AL, remove a vertex from the queue and proceed by examining each of the vertices on the AL. Unvisited vertices are visited and placed on the queue. Visited vertices are ignored. Finish the search when the queue is empty. BFS resembles a level order tree traversal. Void BFS of into E, node W, front is equals to rear is equals to null, printf for percentage dv, then visited of V equals to true, then add Q of V while front V equals to delete Q. For W equals to graph of V W, then W equals to W link. And W equals to graph of V W link. If not visited of W dot vertex, printf percentage D W dot vertex, add Q W dash vertex, then visited of W vertex is equals to 2. True. Connected components. So whether or not an undirected graph is implement this operation by calling either DFS of 0 or BFS of V connected components and determine if there are any universal vertices. Void connected, void int I for I is equals to 0 is less than I plus plus if not visited of I, DFS of I. Spanning tree. When graph G is connected, DFS or BFS starting at any vertex visits all the vertices in G. Such implicitly partitions the edge in G into two sets. T, tree edges, and non-tree edges. T, set of edges used traversed during the search, set of remaining edges. Tree edges, non-tree edges, set of edges used or traversed during the search, set of remaining edges. Spanning tree is any tree that consists solely of edges in the graph that includes all vertices in G. A spanning tree is minimal subgraph G dash of G such that V of G dash is V of G and G dash is connected. Any connected graph with n vertices must have at least n minus 1 edge, and all connected graphs with n minus 1 edges are trees. Spanning tree has n minus 1 edges. Constructing communication like between cities that we will be using as spanning trees. Then cost of the spanning tree is the sum of the costs of the edges of the tree. By connected component, assume that G is an undirected connected graph. The articulation point is a vertex V of such that the deleting of V together with all edges incident on V produce a graph G bar that has at least two connected components. Connected graph but a biconnected graph. 4 articulation points, vertices, 1, 3, 5, 7. Biconnected graph is a graph that has connected graph that has articulation points. A biconnected component of a connected undirected maximal biconnected subgraph H and of G. Graph traversal. The process of visiting each node of the graph systematically in the same order is called graph traversal. Breadth first search (BFS) is a method of traversals that graph from an arbitrary vector, say U. First visit the node U, visit all the neighbor of U, visit all neighbor of neighbors of U. Visit all the neighboring nodes first before moving to the next level. Search terminate when all the vertices are being visited. Point all the vertices reachable from start vertex. Source vertex is A. Then U will be nothing first, then Q. Visiting of adjacent of U, node visited, then Q, DQ. First thing will be we will be visiting A, and adjacent of U is B, C, D, E. Then we will add it everything into the Q. First A, then A only. Then we are DQing it A. All the adjacents of A is B, C, D, E. Nodes visited are A, B, C, D, E. Then we are using B, C, D, E. Then pop it from the Q is B. B's adjacent node is F. Add it to this Q. Then C is popped. C's adjacent is G. Then D, E, F, G. Nodes reachable from source A is A, B, C, D, E, F, G. Int S of 10 equals to 0, so everything. S of 10 we are using it for visited or not. F is equals to 0, R is equals to -1, Q plus plus R equals to U. Print U, S of U equals to 1, while F less than or equal to R, U is equals to Q of F plus plus. For each V, if A of U V equal to 1, if S of V equal to 0, print V, S of V equal to 1, Q plus plus R equals to V, end F, end while. The same thing we have written in the program wise, what B of S equals to A of 10, 10, int 10, int U. Then int F R, Q of 10, V, int S of 10 equals to 0, then print F U R equals to -1, F is equals to 0, Q of a plus plus R equals to U, S of U equals to 1, then print F U while F is less than or equal to R, U is equals to Q F plus plus. If V is equals to 0 is less than V plus plus. If A of U, V is equal to 1, then print that thing, then end everything. Void B of F of node A, the same thing is there. In this node Q list, adjacency list, int V, int S of 10 equals to 0, print U, then Q equals to null, Q is insert here of U, comma Q, S of U equals to 1, print of U, while Q not equal to null, U equals to Q info, Q equals to delete front Q, then list equals to A of U, while list not equal to null, v equals to list info. If s of v equal to 0, then printf that v and s of v make it as 1 visited. So q equals to insert here v comma q, then list equals to list link. Then node insert here node temp, node current, temp is equals to get node, temp is equals temp info is item, temp and link is null. If first is equal to null, then return temp current is equals to first, while current link not equal to null. Current equals to current link equals to temp, return first. Then delete front is node first. If first equal to null, return null. Temp is equals to first. Temp equals to temp link. Temp equals to temp link. Free first. Return temp. Then DFS, depth first search. To search deeper in the graph, U is picked as a source vertex and is visited. The vertex U at this point is said to be unexplored. The exploration of the vertex U is postponed, and vertex V adjacent to U is picked up and is visited. Search begin at the vertex V. There may be still some nodes which are adjacent to U but not visited. When the vertex V is completely examined, then only U is examined. Search terminate when all the vertex have been examined. This first thing is select node U as the start vertex, push U onto the stack and mark it as visited. Add U to S for marking. While stack is not empty, for vertex U on top of the stack, find the immediate adjacent vertex. If V is adjacent, if A is a vertex V not visited, then push it onto the stack and number it in the order it is pushed. Mark it as a visited by adding V to S, else ignore the vertex, and if else remove the vertex from the stack, number it in order of it is popped, end if end while 3 repeat 1 and 2 until all the vertices in the graph are covered. In this, if the source vertex is A, then the adjacent vertex is B, C, D. So node B is visited, node B then it goes to B. After going to B, it goes to adjacent of A is this. Node visited is A. And then stack covers this adjacent of A, then it goes to B. Then that is covered. Then it goes to D. That is covered. Then it goes to F. That is also covered. Then popping off the stack. Depth first search. Then at the end F. Then after that nothing is there. Everything is visited. So pop F. F is popped. Then after that D is popped. Then B is popped. Then instead of popping A, it goes to another adjacent thing, that is E. Then E to G to C. It goes anywhere it's wanted. So then next it goes from that. So E will be popped, then G will be popped, then C will be popped, then A will be popped out. Sorting and searching. Sorting refers to the operation of arranging the same given order, such as increasing or decreasing. Searching refers to the operation of finding the location of the given item in a collection of items. Then complexity of the sorting algorithm measures the running time of the function of the number n of items to be sorted. Complexity function measure only the number of comparisons, since the other operations at most constant factor of this. number of comparisons. Insertion sort. An array A with n elements, A of 1, A of 2, A of n. In memory, scans A from A of 1 to A of n, inserting each element A of x into its proper position in the previously sorted subarray. A of 1, A of 2, A of k minus 1. This algorithm is frequently used when n is small. Play cards. Once the boundary moves to the right, most of the element towards the left of boundary represents sorted list. Word insert sort, that will be int a, int n, int ij item. For I is equals to 1, I is less than I plus plus. Item is equals to a of I. Then j is equals to I minus 1. An item is less than a of j. And j is greater than or equal to 0. Then a of j plus 1 equals to a of j. J is equals to j minus 1. A of j plus 1 equals to item. A of j plus 1 equals to item. Then if we consider radix sort decimal numbers having base 10. There are pockets ranging from 0 to 9. Initially all 10 pockets are empty. Step 1. Scan each item in the list. Obtain the least significant digit, say D. Insert the item into the position at P of D. If an item is already in P of D, then insert the above the last item in P of D. Each item in the list can be inserted into appropriate pocket. Access each item and copy the items present in each pocket one after the other, starting from position 0 through 9 into the original array. Word radix sort. Int a of something, int n. Int ijk big digit. Note p of 10 10. Big largest of a comma n. M is equals to log 10 big plus 1. For j is equals to n, j is less than or equal to m, j plus plus. I is equals to 0 is less than or equal to 9, I plus plus. P of I equals to null. For I is equals to 0 is less than an I plus plus. Digit is equals to separate digit of a of I comma j. P of digit equals to insert rear of a of I comma P of digit. K is equals to 0. For I is equals to 0 is less than or equal to m, 9, I plus plus. Temp equals to P of I, while temp not equal to null. A of k plus plus equals to temp info. Temp is equals to temp link for position I, max by pos greater than 0, pos not equal to 10. Pos into 10. Counts out of this thing. Then you can look into this. Then go with the hashing. Hashing time required to access any element in an array, irrespective of its position, is same. The physical location of ith item in the array be calculated by multiplying the size of each element an array with I and adding it to the base address. Location of A of AI is base of A plus W into ILP. I minus LP. I is the index, W is the size of each element of the array, lower bound. The address of any item at any specified position of I can be obtained, and from the address obtained access the item. Same idea is used in hashing to store and retrieve the data. Create a hash table elements like 10, 11, 12 and all. There are 5 number of items. So h of k, h of any number, hash function is defined as h of any number equals to number modulo size of the table, that is 10 modulo 5 is 0, so it will be fitted in the 0th position in the hash table. A function can be used to provide a mapping bet large original data and the smaller table by transforming a key information an index to the table. The index value returned by the function is called hash value. The function that transforms the data into hash value table is hash function. Hash table, the data can be stored in the form of a table using arrays with the help of hash function, which gives a hash values as an index to access any element in the table. Hashing, the process of mapping large amount of data into a small table using hash function. Hash value and hash table, two types of hashing techniques: static, dynamic. Static, the process of mapping a large amount of data into table whose size is fixed during compilation time. Size of the table usually with a prime number such as 5, 7. Identifiers: ant, dog, cat, eagle, fish, and ape. Construct a hash table to insert identifier starts only with letter A to Z, range 0 to 25. To insert require hash function. A is 65, A minus 65. That is zeroth element and third element, second element. This will be the hash value for this. X of 0 minus 65. 65 is the ASCII value of A. So that's why. A cannot be inserted because an identifier is already placed on that part. This condition called overflow or collusion occurs. The type required to insert, delete, or search depends only on the time required to compute the hash function, and the time to search on the location is hash table of I. Insert, delete, and search times are independent of n, which is the number of items. Hash function. Good hash function satisfy two criteria. Hash function should generate the hash addresses such as that all the keys are distributed as evenly as possible among the various cells of the hash table. Computation of the key by hash function should be simple. Types of hash function: division method, mid-square method, folding method. Converting keys to integers, division. Types of hash function is division method. Choose a number m which is a prime value and it larger than the number of the given elements n in an array. Key item k is divided by some number m and the remainder is used as a hash value. H of k is equals to k modulo m. 97. Then mid-square method. Key is squared. The number in the middle of the k square is selected by removing the digits from both the ends. H of k is L, where L is obtained by removing digits from both the ends. By selecting the middle position of the square number, different keys are expected to different hash values. Like for example, if we square the number 2345, we will get the digit as 5499025. Then we will be using the number 99 as the hash value. And for this 3205, we will get the k square's middle element as 72. So we will be using that. Same positions of k square must be used for all the keys. Folding method. K is divided into number of parts k1, k2 to kn. Same length except the last part. All parts are added together. H of k is k1, k2, k3, kn. Here 1, 2, 3, 9, 8, 7, 2, 3, 4, 8, 7, 6. K1 is 12, K2 is 39 and all. 76. Till 76 if we add we will get 285. Then if that is the number, then we will be adding double digits. If a number is 3205, we will be adding 32 plus 05, that is 37. Converting keys to integers. If key is a string, hash value obtained by converting string into integer done by adding all the ASCII values of each character in the string ABCD. That is 65, 66, 67, 68, 66. Overflow handling, collusions and its detection. If the size of the hash table is fixed amount, the size of the table is smaller than the total number of the keys generated, then two or more keys will have the same hash address or hash value. Hashing techniques used to avoid collusion is open addressing, chaining. In open addressing, the amount of available for storing various data is fixed at the time, any time, by declaring a fixed array for the hash table. All the keys are stored in the fixed hash table itself without the use of linked list. Collusion can be avoided by finding another unoccupied location in the array using linear probing. Create a hash table, initial hash table, select hashing function, find the index of each location in the hash table, assume size of the hash table is 5, store 0 values, then avoid hash table of int array. Int I for I is equals to 0 is less than the hash table I plus plus, here phi is equals to 0. We have initialized it. Then select the hash function h modulo m to compute the hash value, m minus hash size. Then find index of the each location in the for I is equals to 0 is less than hash size I plus plus printf the hash size. Then index to the hash table from h value will be index equals to h value plus I modulo hash size. Insert an item into the hash table using linear probing. Insert an item into the hash table only in the empty position. Word insert int item int a of list int I index h value is equals to h of item. For I is equals to 0 is less than the hash size I plus plus, index equals to h value plus I modulo hash size. If a of index equals to 0, break. If a of index equal to 0, a of index equals to item. Else hash table full. Search for an item in the hash table. Int search int key a int I comma index h value is equals to h of k. For I is equals to 0 is less than the hash size I plus plus, index h value plus I modulo hash size. If key equal to a of index, return 1. If a of index equal to 0, return 0. If I equal to hash size, return 0. Then construct a hash table HTE of size 15 to store the following words like tree, you, find, friend, first to grow and then branch out. Find hash address for each word by taking the sum of the positions of the alphabets. In the word, taking the reminders by dividing it to 15. And 1, 14 and 4 equals to 19. 19 modulo 15 is 4. So it will be kept in the fourth table. Then branch out. Like this. So 37 modulo 15 is 7. So in the same way, equals to 1 means 1 modulo 15 is 1 only. In the position if already filled, insert in the next available location. A is the word is already there. Choose the next location. Here we have written all the hash values for each words. You can refer it once. Chaining achieved using an array linked list. If an item has to be inserted using the hash function, the hash value is obtained. A hash value is used to find the list to which the item is to be added, and using appropriate function, an item can be inserted at the end of the list. If more than one key has same hash value, all the keys hashed into same hash value will be inserted at the end of the list, and thus collusion is avoided. Construct a hash table of the size 5 to show the following words. Arrays of 5 linked list like 12, 9, 11, 5, 37. This modulo 5 will give you the 2. Array of 5 rows with each row having linked list. Hash table with linked list. If there is any collision occurs, then achieved using the array of linked list. It will be fitted in the same position of our address by using the linked list. Add insert h int item node a of this. Int h value is equals to h of item. A of h value, insert here item comma h value. Insert int key node this. Int h value node cur h value equals to h of key. Cur equals to search of key comma hash value. If current equal to null, return 0, return 1. Then void display node a int I node temp. For I is equals to 0 is less than hash size I plus plus. Printf a percentage d is I. Then temp is equals to a of I. If temp equal to null, printf null. Else temp equals to a of I. While temp link not equal to null, printf percentage d. Temp information. Temp is equals to temp link. Address calculation sort called hash sort. To find the hash value, int hash, int a, int n, int big I pos equals to 0. For I is equals to 1, I is less than n I plus plus. If a of I greater than a of pos equals to I. Big equals to a of pos, I is equals to log 10 of big, then return power of 10 comma I. Address calculation sort is sorting method which sort this. These are all not there in the syllabus. You can skip these. Thank you. If you want, you can study these things.
Thank you for watching. Do like, share and subscribe to my channel.